Okay, so I'm going to explain how my Lstm made to the romanization of Korean works. So first of all, the romanization is the process of converting a non-Latin script to the Latin script, usually then converting the sounds, okay, basically, if we could put into just a few words. But there's a lots of applications: learning new languages, adapting boards and signs for travel places, academic studies, and which for me it's the best, the modern keyboards for non-Latin languages. As you can see in the GIF, it's a Chinese keyboard. You type Latin script and it converts to the ideograms. It doesn't translate, it just converts the sounds. It's very cool and complex. And computationally speaking, this is a context-sensitive grammar, which means that the rules to transform one character into another depends not only in the character or the sound of individual character, but by the context, by the other characters in the same string, and sometimes in different strings. As you can see here, A becomes gamma only because there's alpha and beta besides it. Because if it was a different character, A wouldn't be translated into gamma, would be translated into something else. Very simple, I think. Our role to Lstm. So deep learning is not only about fitting a net with data, but splitting, normalizing, and encoding this data, which is basically the process of formatting this data. Okay, so let's get into the first step, which is splitting. So the input-output pair we are using is this one, and the JAMO is split using the JAMO tools library. Okay, you'll be able to use that if you download our repository. Here you can see the JAMO, which is composed by 3 letters being converted into a list of 3 letters, and the same for the romanized version. The normalization process is the process of making those lists the same length by adding null components or neutral components, as you can see here. And then you encode it. If you use the same library as we do, the vectorization is predefined. So each letter and each Hangul, each JAMO, and so on have a specific number. It's just used to fit the net, because the net doesn't recognize the character itself, but a number, so that they can work mathematically with it. So you can see here. Here, we can run this data to generate the training set. So the training set we've chosen here was a 100 rounds. So it generates a data like that, which is a Hangul as here, the romanized version of that Hangul or JAMO. And you can see the vectorization of both. Nice. And here we are talking about the Lstm properly, okay? So the Lstm is a long short-term memory. It's more flexible, can deal with larger memory sets and larger input sets, and usually strings, okay? But not only. The system is basically composed, as you can see here, by little nets. So each of those cells is a net that have a stage H here, stage H. Which takes X and input and pass its states to the next cell, which takes X2 as input, and so on and so on and so on. That's why it's a long short-term memory, because at the same time it has a short memory, because every input have a actual output. Always the next input needs the input before to get its output, okay? It's a little confusing because it's the first time you're probably seeing it, but with this animation, you'll be able to get it. Look at this. So we fit, the state passed to the next cell, and as you can see here, there are little nets which make the state, and you pass to the next state, which became the next state, and the next, and the next, and the next. So the last, for example, the last character of the string won't have a random output, but a output depending upon the other inputs, you know? So that makes the LSTM perfect for the context-sensitive grammars, okay? And here we run this code, which is the net properly speaking, okay? And you can see everything here, but you can see every of this in the repository, okay? In both in the Jupyter and the Py files. Here, here we used the Hangul one as the input. So from all the training data, we get the first one to be our input. 10 rounds of training, which is very little. It's just a toy net here. It loaded, okay, as you can see here. Took 3 seconds to train it, almost nothing to predict. And it predicted correctly, as you can see here. Okay, expected GAC and get GAC, similarity of 100%. Okay. Let's see the error. As you can see here, the error is very huge if you compare to other networks. Why? Mainly because we trained it very little, okay? So the error will be high, okay? So the more you train, the less error you have, okay? But just because it's a toy net, we don't need to worry about it. But you can use this script to see the errors, okay? And here are our references. And here you can see that I put it per 6, and you can ask yourself, why per 6? Because we've made a fun thing that you'll be able to see in the next video.